In public health research, we often want to compare the average value of a health outcome between groups. For example, is average BMI different between males and females? Does a treatment reduce blood pressure? The t-test is one of the most commonly used statistical methods for answering these questions. In this video, we'll learn when to use independent and paired t-tests, how to perform them in R, and how to interpret the results in a public health context. So when exactly do we use a t-test? Well, a t-test is appropriate when the outcome variable is continuous. We want to compare means and the data are approximately normally distributed. There are two main types: the independent t-test, which compares two separate groups. Example, BMI in smokers versus non-smokers, and the paired t-test, which compares measurements from the same individuals. For example, blood pressure before and after treatment. As usual, we start by loading the necessary libraries: readr to import the dataset, dplyr for data manipulation, and ggplot2 for visualization. Then we load our NGENS sample dataset. First, we create a box plot of BMI by sex. This gives us a visual sense of whether BMI distributions look different between males and females. In public health research, visualizing group differences is an important first step before running statistical tests. We want to see, do the medians look different? Is one group more variable? Or are there extreme values? Visualization helps us understand the data before relying on p-values. Next, we calculate the mean BMI for each sex using group underscore by and summarize. This gives us the average BMI within each group. We use na.rm equals true to remove missing BMI values from the calculation. Let's say we are trying to answer the research question: is average BMI different between males and females? To do this, we would run an independent t-test using t.test BMI tilde sex. This tests whether the mean BMI differs significantly between two independent groups, in this case, males and females. So let's do a little bit of unpacking of the information we have here. First, this is a Welch t-test, which is a version of the independent t-test that does not assume equal variances between groups. In real-world public health data, variances are often unequal, so Welch's test is generally a safer default. So we see C equals minus 0.11764. What does this mean? Well, the t-value measures how large the difference between group means is relative to the variability in the data. Here, the t-value is very close to 0. That already suggests that the difference in mean BMI between females and males is extremely small relative to the overall variation in BMI. Next, the degrees of freedom, or DF. We can see DF equals 2337.2. This reflects the sample size and variance structure. A large value like this suggests we have a relatively large sample, which increases statistical precision. Next, p-value equals 0.9064. This is the key number for hypothesis testing. The null hypothesis states that the true difference in mean BMI between females and males is 0. A p-value of 0.9 is very large, much larger than the typical 0.05 threshold. This means we fail to reject the null hypothesis. In plain language, there is no statistically significant difference in average BMI between females and males in this dataset. Next, we look at the 95% confidence interval, minus 0.418 to 0.371. This interval represents the range of plausible values for the true difference in means. Importantly, the interval includes 0. That reinforces the conclusion that there is no meaningful difference. It also tells us something practical. Even at the extremes, the true difference is likely less than half a BMI unit in either direction, which is very small from a clinical perspective. Finally, we look at the actual group averages, mean BMI in females, 26.93, and mean BMI in males, 26.95. These numbers are almost identical, differing by only about 0.02 BMI units. So the statistical result matches what we see in the raw averages. There's essentially no difference. From a public health standpoint, this suggests that in this sample, BMI levels are similar across sexes. That does not mean sex never influences BMI. It simply means that in this specific dataset, there is no evidence of a difference in average BMI. However, it's very important to remember, not statistically significant does not prove equality. It simply means we do not have evidence of a difference. Paired t-tests are used when measurements come from the same individuals at 2 time points. For demonstration, we'll simulate a before and after blood pressure dataset. We create 2 small vectors, before and after. These might represent systolic blood pressure measurements before and after an intervention. The key difference is that these measurements come from the same individuals. That means the observations are related. We run the code t.test before, after, paired equals true. Now let's walk through the results of this paired t-test step by step. We see t equals 9.5618. This is a large t-value. The t-statistic represents how large the observed mean difference is relative to the variability of those differences. A value this large suggests that the change from before to after is substantial compared to the natural variation in the data. df equals 4. Since this is paired data with 5 individuals, the degrees of freedom are calculated as n-1, which equals 4. This tells us the sample size is small, only 5 paired observations. So we should interpret the findings with caution, even though the statistical result is strong. P-value equals 0.00066683. This is a very small p-value, well below the common threshold of 0.05. This means we reject the null hypothesis, which states that the true mean difference between before and after is 0. In simple terms, there is strong statistical evidence that the intervention or change between the 2 time points had a real effect. Next, we look at the 95% confidence interval, 5.68 to 10.32. This interval tells us the plausible range for the true mean difference. Importantly, the interval does not include 0. It is entirely positive. This reinforces the conclusion that there was a meaningful increase or decrease, depending on how the difference was calculated. If this represents blood pressure before minus after, for example, it suggests the intervention reduced blood pressure by somewhere between about 6 and 10 units on average. Finally, we see mean difference equals 8. This means that, on average, the outcome changed by 8 units between the before and after measurements. So what interpretation would we give to these results? Well, even with a small sample, the effect appears statistically significant, consistent across participants, and meaningful in magnitude. However, because the sample size is only 5 individuals, this result should be viewed as preliminary. In real-world public health research, we would want a larger study to confirm the findings. And that brings us to the end of the video. We successfully visualized differences between groups, calculated group means, tested for statistical significance using an independent t-test, and compared before and after data using a paired t-test. Together, these steps demonstrate a basic but important workflow in public health data analysis: visualize to summarize to test to interpret. Understanding not just how to run these tests, but when and why to use them, is essential for making valid and meaningful inferences from health data. In the next video, we'll extend this idea to comparing more than 2 groups using analysis of variance, or ANOVA. This method is widely used in epidemiology and public health research when comparing multiple populations.